So we're ready to begin the second part of our course. There's really three parts of our course. So the first part of our course is saying, well, let's learn a little bit about derivatives, understand how they work, understand the basic rules. So we had to do limits. We went from limits, we said, okay, let's find all these good rules. So we developed rules like the product rule and the chain rule and other rules. And we said, let's develop a set of functions, so like exponential and trigonometric and polynomials. So we have some set of wonderful tools. Now in the second part of the course, we're going to add a little bit more. So there's a few ideas that are going to happen this week when we say, okay, let's really round out our set of tools. So we're going to talk about interesting functions over the next couple of days. And then comes the fun part, applications. And we're going to see, okay, why do we care about the derivative? And the spoiler alert is we care about derivatives because derivatives tell us how things change. And oftentimes, if we know how things change, we can get information. So for example, we can figure out when is the best thing, the optimum. And that's in the weeks to come. So we're going to start with today talking about explicit functions versus implicit functions. Now an explicit function, these are the kinds of functions we've been dealing with, where we have y equals stuff with x. Now there's really nothing sacred about the symbols y and x, just one variable depends on the other variable. And this is how we oftentimes think of our functions. So if you think about how we have here, we're like, well, you have your little machine, and what's happening is you're feeding your machine in with your input. So in comes x, you run it through the process, out comes y. So that's how we oftentimes think of what's happening. We throw x in, it follows a recipe, out comes y. But there's other ways to think about functions, and there's other ways to get relationships. So there's another thing called an implicit relationship, where that is, you have stuff with x and y is equal to other stuff with x and y. So you may not necessarily be able to solve y explicitly. So what does that mean? Well, does it mean that y is not a function of x? And the answer is no. Y will still depend on x. It's just we can't get a nice formula for it in all cases. So let's take a look and talk about which of these are not explicit functions. Okay, so y equals x squared. Actually, let's just put them all out here. X squared plus sine of e to the x times cosine of square root of x squared plus 1. Explicit or not explicit? Explicit. Okay, so that's fine. Okay, so that's not explicit. Oh, wait. Yeah, not explicit. Explicit. Okay. Why? Well, because notice on this side over here, it's just stuff involving x. So that's great. How about x squared plus y equals e to the x plus 17? Well, it can be made explicit. The form it's in now is you really haven't gotten y by itself. So when we think explicit, we said y by itself is stuff with the other variable. So as it's written, it's not explicit, but through the use of modern technology, we can move the x squared across to make it explicit. Okay, now on to the next one. Sine of x plus e to the y equals x squared minus cosine of y minus y. Explicit or not explicit? Not explicit. Okay, this one, there's no hope. There's no way to solve for y by itself. Essentially what's happening here is you see like these parentheses here where y is being plugged into, for example, the cosine. And on the other hand, there's y that's on the outside of that cosine. Those bars, they're like prison bars. You know, you can't free them so easily. And so there's no way to get y by itself. Nevertheless, should you choose a value for x, it says something about what y can and cannot be. How about here? Y equals 5t squared plus cosine t minus e to the minus t. This is explicit. Now here the slight difference is we've just changed our variable name. So instead of stuff with x, it's stuff with t. But that's okay. Names can be changed. That's fine. How about x squared plus y squared equals 25? Explicit or not explicit? This is not explicit. Now, let's actually talk about this because x squared plus y squared equals 25. We actually know what this looks like. What is it? Yeah, it's a circle, right? Now, if you draw a circle, it looks like a circle. So, not a big surprise. Can this be a function? No, because there's something called the vertical line test. And what you do is you draw a vertical line. And if you hit it twice, that says, oh, see, for a single x, it can't make up its mind which y value it is. So this cannot be a function. You cannot write this relationship as y is a function of x. You can, however, break it apart. So there is no way to write this as a single expression, y in terms of x. What are the two expressions you could write? Do you know? Well, if you move the x squared across and took the square root, you get y equals the square root of 25 minus x squared. And what would that be? It would be the top. But when you take square roots, you could have done plus or minus, which is the bottom. And so you can't get here an explicit relationship. X cubed plus xy minus 2y squared equals 7. Explicit or not explicit? This is not explicit. Can't solve for y. All right, how about the bottom one? X equals 5y squared minus cosine y. Explicit or not explicit? It's explicit in the following sense, in that we've solved for x in terms of the other variable. Again, names aren't important. We can change names around. So this is an explicit relationship for x in terms of y. All right, well, good. Now we can recognize them. Now we're going to need a nice idea to help us work with these functions. And our nice idea is actually pretty simple. It's so simple that you may not realize how useful it is. Here it is. If two functions are equal to each other, then their derivatives have to be equal to each other. Now that sounds not very surprising. It says, hey, you know, if I take the derivative of the same thing, I should always get the same answer back. So at first hearing that, it's like, okay, how can we use it? Let's actually test this. Well, here I have two functions of theta. Cosine squared theta plus sine squared theta. And then I have this other function called 1. Well, is it true that cosine squared theta plus sine squared theta is equal to 1? Yes, good. That's one of your 6 trig identities you should know. All right. Well, let's verify that f prime of theta equals g prime of theta, which means we need to take the derivative of these two functions. Well, idea. All right. Let's take the derivative of g first. So, what is g prime of theta? Derivative of 1. 0. That one's not so bad. How about f prime of theta? Well, derivative of cosine squared theta. What's our rule? Chain rule, because it's a cosine is on the inside the square. So according to the chain rule, what's the derivative of cosine squared theta? 2 cosine theta to the 1. Anything else? Times negative sine, because you got to take the derivative of the inside. Now, come to the derivative of sine squared theta. What is that? 2 sine theta to the first times positive cosine. The derivative of sine is positive cosine. Now, we have to check. The claim was that these two should be equal. And you might notice that one of them is a lot longer to write than the other. However, there's something that's very useful for us. Namely, that negative there is very useful. And so when we put those together, what do we get? They'll cancel out. Because you have 2 times cosine times sine, but with a negative. Here you have 2 times cosine times sine, but it's positive. So they do in fact match. All right, well, how are we going to use this idea? Well, here's what we do. So when we have an implicit relationship, it's still a relationship. So what that means is our inability to do algebra and do manipulation doesn't mean that it can't theoretically be done. So what we're going to do is we're going to say, well, let's suppose that we could. Well, we can't, but we're going to suppose that we could. And we're going to think that y is a function of x. So whenever we see a relationship, an implicit relationship, we're going to say, you know what? Y is some function of x. I just don't happen to know what that function is. And now, once you have that, take the derivative of both sides with respect to x and use the chain rule. All right, that's the idea. So let's work through an example. So first off, when I see x squared plus y squared equals 25, I again say, well, y I'm going to think of as depending on x. So there's some function, quote unquote, y of x. Now we know that there's not an explicit function that does it. But for right now, we're going to think of there's some function y as a function of x. So we're going to think of x squared plus y of x squared equals 25. Now, take in the derivative of both sides. So, the derivative of x squared, 2x. The derivative of y of x squared, well, what rule do you need? Chain rule. So it would be 2 comes down, y of x to the first, times the derivative of y with respect to x. And here's the key. The derivative of y with respect to x is the derivative of y with respect to x. So that's, you got to remember that, okay? So if you ever get to a point when you say, okay, what's the derivative of y with respect to x? The answer is it's the derivative of y with respect to x. Now that's the derivative of the left-hand side. That has to match the derivative of the right-hand side, which is equal to 0. Now, what can you do? Well, you can think about it in the following way. Well, I can solve for the dy dx, so that's what I'm interested in. What's the derivative? So dy dx would be move the 2x across and divide by that 2y of x. You get negative 2x over 2y of x, or negative x over y. So I can now answer the question, if I want to talk about what's happening on the circle, and in other words, what's the rate of change going on, the slope of the tangent line at a point, I can answer it by looking at this relationship here. So the nice thing about this is it actually works regardless of where on the circle. Well, that's a terrible. You have to imagine that's actually a circle there. But it works regardless of where you're at on the circle. So if I'm over here at this point, I want to say, well, what's the tangent line? What's the slope? Well, the answer is, well, suppose I'm at a point. Now, this is a circle with 25, so suppose I'm at the point 4, negative 3. X equals 4, y equals negative 3. How can I find the slope? Well, use the formula. So the slope is going to be negative the x value over the y value, so we get 4/3. And that matches with our intuition. We can also kind of verify this in a sort of an indirect way, which is we could do this the complicated, use the formula. So if we tried to solve for y, explicitly, square root of 25 minus x squared, and then we took y prime, well, this is the same as 25 minus x squared to the 1/2 power. This would be 1/2 comes down, 25 minus x squared to the minus 1/2 times the root of the inside, which is minus 2x. 1/2 times minus 2x would leave us with a minus x upstairs, and downstairs is the square root of 25 minus x squared, because that's the minus this 1/2. But the square root of 25 minus x squared is y, which is minus x over y. Now the reason you might say, okay, well, we got the same answer, why is this better? Well, it's better because this argument, where does it apply? It applies only for the top half, because that's what the curve is. So we'd have to repeat the argument for the bottom half, which means we'd have to double the amount of work. But regardless, it turns out you'll still get the same thing if you work it through on the bottom half. So this is actually a really nice process. It's very simple, it's very clean. And this is known as what's called implicit differentiation. Okay. Oh. You just did the example here. Whoops. All right. Should we redo it? No, come on. We don't need to do it again. All right. So here we go. We'll skip the example. So what are the highlights of implicit differentiation? Take the derivative of both sides with respect to one of the variables, whichever one you want to know. Make sure you apply the chain rule correctly. And for the make sure you apply the chain rule correctly, that's the think of y as being a function of x. And then after taking the derivatives, carefully rearrange and solve for your desired derivative. All right. Well, that's not so bad. We can do these. So let's see. Find dy dx given y cubed plus e to the xy equals 1. So this is something where we can't solve for y in terms of x. It is possible to solve for x in terms of y, but that would be if we wanted dx dy. That's a different session. That's not for today. All right. So find dy dx. Okay, so step one, we're going to take the derivative of both sides with respect to one of the variables. In this case, what are we taking the derivative with respect to? We're taking the derivative with respect to x. What's the clue that we're taking the derivative with respect to x? Yeah, the fact that it's dy over dx, whatever's downstairs, that's what you're taking the derivative with respect to. So the way you read the notation is derivative of y with respect to x. So we're taking the derivative with respect to x. So we're going to take the derivative of both sides with respect to x. Now, we don't write this down usually, but because we're new at this, we're going to do it just this one, maybe two more times. So y of x quantity cubed plus e to the x times y of x equals 1. So that's what we're going to think of. Even though we don't know what y of x is, we're going to think of it as though we had it. And we're going to manipulate it that way. So, again, this is mentally done in our minds. So let's work our way through it. Y cubed plus e to the xy equals 1. All right, let's start by taking the derivative of the left-hand side. What rule do we need to take the derivative of y cubed? Okay, power rule. Special case of the chain rule. Derivative of y cubed is going to be 3y squared, right? There's more to it. Because you remember, we're taking the derivative not with respect to y, but with respect to x. So it has to multiply by the derivative of the inside. In our case, the inside is y. The derivative of y with respect to x is dy dx. Or, if you like shorthand notation, you could also write y prime. Both are fine. Dy dx or y prime. All right, now let's go to e to the xy. What's our rule we're going to need? Chain rule. The derivative of e to anything, well, it's e to that thing, times the derivative of xy. What rule do we need to take the derivative of xy? Product rule. Okay, so the derivative of x is 1 times y, so that would become y, plus x times the derivative of y, which is the derivative of y. So anytime we get to a point where we have to say the derivative of y, we write down something which stands for the derivative of y, either y prime or dy dx. Now, we're not done because, remember, we have to take the derivative of both sides. We only take the derivative of the left side. Now we have to do the whole thing over for the right side. What's the derivative of 1? Yeah, usually one side is easier than the other. All right. Now, our goal here is to find our y prime, to find dy dx. So, how do we do that? Well, the answer is, if we've lived a good life and followed the rules, what we can always do is we can get all the y primes together. So, we take a look and say, where are the y primes at? Well, in this case, there's a y prime here and y prime there. So So what we're going to do is have everything with a y prime on one side of our equation. Everything without a y prime goes to the other side of the equation. So let's see, what would we have? Well, if we keep the y primes on the left, 3y squared y prime, then remember that this e to the xy will distribute through. So I just want the part with the y prime. So plus x e to the xy, y prime. Now there's still an e to the xy times y. That doesn't have any y prime, so that's going to move across. So that'll equal negative y e to the xy. So everything with the y prime to one side, everything without a y prime to the other side. Now what? Factor the y prime out. So 3y squared plus x e to the x times y prime equals negative y e to the xy. All right. Well, almost there. Remember, what were we looking for? We're looking for getting y prime by itself. So what's our last thing? Divide through. Yeah. So y prime is equal to negative y e to the xy. Divide that by 3y squared plus x e to the x. Somebody pointed out, I made a mistake. What happened? Well, when I factored, notice how we have e to the xy, and down here it became e to the x. I forgot the y. What does that mean? Why is that? Well, because I didn't pay attention. Mistakes can happen. Don't! Well, be careful, be careful. You'll never fully get past your mistakes, but the more you practice, the fewer you'll make. We've talked about taking a derivative evaluated at a point. Now you might have the case where you want to take a derivative which is an implicit derivative. So we have, for example, y prime is something involving both x and y. And you might say, okay, can we now take the derivative at a particular xy point? And yes, you can. The way that's often denoted is you take dy dx, evaluate it as. So if you ever see a straight line up and down, that's just a code for evaluate. So evaluate this at the point AB. All right, so we have an example. Find the tangent line to the implicitly defined curve. X cubed plus y cubed equals 9xy at the point 2, 4. And it says, let's find the slope in two ways. Ooh, interesting. One, explicitly solve for dy dx and then evaluate. And two, after taking the derivative, evaluate and then solve. So there's this sort of back and forth. There's this play going on. And the question becomes, well, when do you evaluate? So this is a good question to ask. Now, we're going to hopefully find out from this what the answer is. But in general, what's the right question for, like, when do we evaluate? So the general answer is the time to evaluate is as soon as possible. So if you have a problem and it says, I want to know what it is at a certain point, evaluate as soon as possible. But there's a catch, not sooner. So sometimes when you see an evaluation problem, you're like, oh, let me start by doing my evaluation right away. And you say, wait, you can't do it right away. You can't do it right away. All right, so let's go through and see what happens here. Okay, so we're going to find the tangent line. Now, if I'm looking for the tangent line, what information do I need? Slope and point. Do I have either of those? I have the point. Now, one thing we should be a little bit cautious of, is this point actually on this curve? How can we check? Plug it in and see if it satisfies the relationship. So, does 2 cubed plus 4 cubed equal, question mark, 9 times 2 times 4? Well, 2 cubed is 8. 4 cubed is 64. Does that equal? Well, 9 times 2, 18 times 4, 72. And, oh, it does. Okay, good. So the 0.24 is on this curve. I'm not sure what the curve looks like, but it's there. It's one of probably many points as far as we know. Okay. So, all right. So, okay, so we need the slope. All right, find the slope in two ways. So let's solve for dy dx. So take the derivative of both sides. Derivative of the left-hand side, derivative of x cubed, 3x squared, derivative of y cubed, 3y squared, dy dx, or y prime. Okay, equals, now take the derivative of the other side, derivative of 9 times xy. Well, 9, I like to do 9y because I think of the derivative of the x first. Derivative of x is 1. Plus, what's the other term? 9x dy dx. Which I'll write as y prime. All right, so that's a universal step. So we can't evaluate. So in other words, I can't plug in the point 2 comma 4 first and then take a derivative. Because if I plug in 2 comma 4, I get 72 equals 72. If I take the derivative, I get 0 equals 0, which doesn't tell me any information. That's what the not sooner part is referring to. But once I've taken a derivative, I can evaluate it at that point. But we're going to step back and do option 1. So option 1, okay, explicitly solve for dy dx. So we're going to move the term with the y prime across and the term without a y prime across. So if we do that, we'll get 3y squared y prime minus 9x y prime will be equal to 9y minus 3x squared. But of course, from here, we can factor a y prime out. So we're going to get 3y squared minus 9x times y prime. So, dividing, we get y prime is equal to 9y minus 3x squared divided by 3y squared minus 9x. Okay, so that's dy dx. And that's our expression for any choice of x and y. Now what happens? Well, we've solved for dy dx, and now we evaluate. So, I'll do it over here. Dy dx at 2, 4 is going to end up being 9 times 4 minus 3 times 2 squared divided by 3 times 4 squared minus 9 times 2. So everywhere we see an x, we plug in 2. Everywhere we see a y, we plug in 4. And now we hope that it simplifies reasonable. 9 times 4? 36. 3 times 4? 12. 3 times 16? 48. 9 times 2? 18. 36 minus 12? 24. 48 minus 18? 30. And can you simplify 24 over 30? Yeah, what do you get? They both have 6, so you end up with 4/5. All right, now that was option 1. Option 2 says, actually before you start solving, let's evaluate. So we took the derivative, and now before we do anything else, we're going to plug in numbers. So we're going to get 3 times, plugging in 2, so it's going to be 3 times 4, well, I'll write out 3 times 2 squared, plus 3 times 4 squared y prime. And I really should say this is y prime evaluated at the point, but for notation, we won't do that. That's going to equal, and what's the other side? Well, 9 times y, so that's 9 times 4, plus, then here we'll get 9 times x, which is 9 times 2 times y prime. Now at this point, we can say, okay, now what happens is instead of manipulating just symbols, we just have to manipulate numbers. So it's the same numbers involved if you look at the numbers here, but now it's much easier for us to play with. We can say, oh, move the 18 across, move the 12 across. 48 minus 18 would give us 30 y prime. And then 36 minus 12 gives us 24. So y prime equals 24 over 30, which equals 4 over 5. So we get at the end the same answer for the slope, whether we evaluate at the very, very end of the process versus if we evaluate as soon as we can. But in some sense, I think it's easier to do the manipulations if you evaluate as soon as you can. And it gets even more prominent the more complicated the expression becomes. Are we done with this problem yet? Not yet. What do we need to be done? We need a tangent line. We've been talking about the slope, so we actually should finish the problem and say, okay, well, to finish the problem, we have the point and we are in our slope. So y minus the y coordinate, which is 4, is equal to our slope, which is 4/5, times x minus our x coordinate, which is 2. So there we go. So y minus 4 equals 4/5 times x minus 2. All right. So a normal line to a curve is a line which passes through the point and is perpendicular to the tangent line. So, in this problem, it says, find the normal line to the implicitly defined curve x cubed plus y cubed equals 9xy at 2, 4. Well, what should we do? We can do a lot of work, or we can do a little bit of work. I like to do a little bit of work. I'm definitely pro, let's make life easy. All right, so how do I know if two lines are perpendicular? What's true about their slopes? They're negative reciprocals, right? Okay, so if I want to find the slope of the normal line, what do? Well, the answer is I take negative 1 over the slope of the tangent line. So that's the fact that they're negative reciprocals. All right. Do we know the slope of the tangent line for x cubed plus y cubed equals 9xy at 2, 4? Yeah, we just found it. So that says for us, the slope of our line is going to be negative 1 over 4/5, which becomes negative 5/4. And once we have our new slope, we still have the same point. So we get that y minus our y value is equal to our slope, negative 5/4, x minus our x value. Not sure why I put parentheses there, but they're not wrong, so okay. And there you go. So finding a normal line is just as easy as finding a tangent line. It's the same amount of work. All right, well, that's good. We've had one derivative, but what about second derivative? Okay. Well, so suppose we have that x cubed plus y cubed is equal to 9xy. And we want to find the second derivative. Now you might say, well, why do we care about the second derivative? Well, it gives information about the curve, and it might be useful to understand that information. So, okay, so we want to find the second derivative of y with respect to x. Well, what's the first step? Well, if you want the second derivative, you should find the first derivative. Now, we could repeat some of our work, or we can just say, hey, we did some of this work. So, because it's the same curve, so we can copy stuff down. So we could say, for instance, we have the following two things which are true. 3x squared plus 3y squared y prime is equal to 9y plus 9xy prime. But we also have somewhere, where is it? Oh yeah, here it is. We also have, this was a rearrangement, y prime equals 9y minus 3x squared divided by 3y squared minus 9x. So these are the two facts as we currently know them when it comes to the first derivative. How do we get to second derivative? Sorry, what? Yeah, to get to the second derivative, we will take a derivative of a derivative. Now, there's two options. Should we do both? Okay, if you insist. Well, let's suppose we say, hey, here's this second option. Y prime is 9y minus 3x squared over 3y squared minus 9x. And we take the derivative of both sides. What's the derivative of y prime? Y double prime, which is what we want. So we could say, aha, this is y double prime is equal to, what rule do you need for this side? Quotient rule. Ah, good times. So the quotient rule says take the bottom, 3y squared minus 9x, times the derivative of the top. Okay, what's the derivative of 9y minus 3x squared? Nine, derivative of y with respect to x, minus 6x. Okay, the bottom times the derivative of the top, minus the top. Well, the top, that would be 9y minus 3x squared times the derivative of the bottom. What's the derivative of the bottom? 6y times dy dx, y prime, and minus 9. All that divided by the bottom term squared. Okay, now suppose I actually wanted to solve for y double prime as a function of x and y. I probably shouldn't, but suppose I did. Where could I go next? So the y double prime is good. What don't we like? We don't like the y primes because we want to have it just as a function of x and y. So how can I get rid of the y primes? I can take this expression for y prime and plug it in. So we get 3y squared minus 9x times 9 times 9y minus 3x squared over 3y squared minus 9x minus 6x minus 9y minus 3x squared times 6y times 9y minus 3x squared over 3y squared minus 9x minus 9. All over 3y squared minus 9x squared. Now at this point you're probably thinking, yeah, but you know what? I don't like fractions within fractions. I'm with you there. How do we solve that problem? Well, the fractional part upstairs is that 3y squared minus 9x. So let's multiply top and bottom by 3y squared minus 9x. So we'll end up with 3y squared minus 9x. Then I'll get 9 times 9y minus 3x squared minus 6x times 3y squared minus 9x minus 9y minus 3x squared times 6y times 9y minus 3x squared. Oh, I'm going to run out of space. Minus 9, and that 9 is being multiplied by 3y squared minus 9x. Okay. All that over 3y squared minus 9x cubed. All right. Now, if we were really crazy, what would we do? Yeah, we'd keep going, right? But remember, what are we after? We're after the derivative at 2, 4. So what can we do now? We could plug in 2, 4. And at this point, you're like, no, that's not happening. I'm not doing it. I'm not doing it. Okay, well, the question is, do we have a better option? You should probably think, I think there's a better way. Because there's a better way. Now, one thing is, we don't actually have to solve for y double prime explicitly in terms of x and y. So that's certainly one thing that's a better way. Let me cover up this monstrosity here. All right. We started by taking a look at the second part. Let's do the first part. Because in the first part, there's no quotient rule. So let's take the derivative. And that, what looks like a b is really an x. All right. So here, derivative of 3x squared, 6x. Derivative of 3y squared times y prime. So let's take the derivative of the first term. The 3 comes along. The derivative of y squared, 2y. Anything else? Times the derivative of y, which is dy dx y prime, times y prime. So there's a y prime coming from two places. The second y prime comes from that y prime that already is there. This other y prime comes along because of the chain rule. Plus 3y squared times the derivative of y prime, which is y double prime. That's going to be equal to, okay, what do we get here? 9y prime plus, what do we get here? Okay, so I would start by saying derivative of x is 1, so the derivative of x times y prime, so that's 9y prime, plus 9x times the derivative of y prime, which is y double prime. Now, we could solve for y double prime here, but we're not going to, because what are we ultimately going to do? We're going to evaluate at 2, 4. So, since we know we're going to evaluate, after we've taken our derivative, let's plug in our numbers. So, remember, what do we know? We know the following. We know that x equals 2. That's the 2. We know that y equals 4. That's the 4. We also know one other thing. We know what y prime is. Why? Because we found it. That was the number we found just a little while ago, 4/5. So, we can plug in all those numbers. So, let's go through and plug them in. 6 times 2, 12. Plus 6 times y, which is 24, times y prime squared. So that's going to be 16 over 25. All right. 3 times 4 squared, well, that's 48. Y double prime. We don't know what y double prime is. Equals 9 times y prime. That's 4/5. Plus another 9. Oh, we should put those together. Oh, well, live and learn. Okay. Plus 9 times x. So that would be 9 times 2, which is 18 y double prime. Now you have numbers to work with. The numbers, well, they're numbers. They're a little bit easier. So we can do some things. So for example, move the 18 y double prime across. That would leave us with 30 y double prime. Okay, let's do a little bit of math. Might as well. It's a math class. 9 times 4 is 36. And we have 2 of those, so that's 72 over 5. 24 times 16 is a number. No, hold on. We can do better than that. We can do better than that. 24 times 16 is 384. Is that, are we close? Yeah, 384. Okay. All right. 384 over 25. Okay. All right. And then minus 12. But, of course, we can clean this up. Multiply common number would be 5, so that would be 72 times 5. That one's easy. That's 360 over 25 minus 384 over 25. And then if we want to get 12 over 25, Well, 12 times 25 is, I think, 300 over 25. Okay, so we're almost there. Let's see. So we have 360 minus 684. Now you're probably thinking, do we have to simplify on the test? No. But isn't it fun when you get to do arithmetic? You're like, yes, I finally, my second grade teacher said someday I'd have to add numbers. They were right. Okay, 360 minus 684. What does that leave us with? Negative 324. 25ths. But remember, that's 30y double prime. So we get that y double prime is negative 324 over 25 times 1 over 30. And you might say, well, does 30 go into 324? Well, 324, it turns out, is equal to 6 times 54. And 30 turns out to be 6 times 5. So you can cancel off some 6's. So we end up with negative 54 over 125. Good. Done. And that's our second derivative. Okay. Well, at least it's nice to know we can do it.